My talk today is about related to free space quantum communication and satellite quantum communication, but I don't want to talk much about the satellite project. I will give a quick intro on the Canadian mission that we have in the works, but rather I want to look a little bit beyond what we're doing right now with space, but look at novel directions of how to do free space communication, which may lead into future missions or future systems. But first of all, I will do the usual introduction or motivation of why we care about quantum satellites. I should say quantum communication satellites. So the big vision is this quantum internet, right? This is this network that we'll have one day in the future, where quantum bits are shared between different users, different stations over long range and short range links, right? And there'll be different systems like, like cities and houses and movable systems. There will be short range systems or longer range to aircraft. And my particular interest has always been long distances, right? How far can we send these quantum signals and quantum entanglement? So that's where satellites come in. Satellites, I think, will play a major role in the future quantum internet because it provides this long-distance bridge, right, which can connect across a continent or even globally. What will this quantum internet be useful for? So secure communications is the first obvious application, and it's also maybe one of the most commercially advanced, let's say, quantum protocols that we have. Interestingly, things like applications like quantum money, which relate to authentication of information might come in, or authentication of systems. Actually, historically, quantum money, the ideas of quantum money predate QKD. But quantum computing, I think those are the really interesting applications as well, and more advanced ones. It's about interfacing quantum computers once they exist, or even quantum computing in the cloud can be a thing, right? So blind quantum computing is a big research area where a remote user could send their information to a quantum computer for processing, and it can be even encrypted in a way that the quantum computing provider can't even read out the information, and they can even encrypt the code, the algorithm, right? So it could be very interesting. And definitely a need for this quantum communication network. I always like to make a fun remark about quantum money. This is the Austrian 1,000 shilling notes, which the currency in Austria prior to euro was shillings, and we had Erwin Schrödinger printed on there. So we had our kind of own version of quantum money in Austria. And finally, there will be applications of such a quantum network, quantum internet, that don't even relate to the typical, quantum processing or information processing applications, but rather to sensing or metrology. So two examples are clock synchronization, or maybe better, let's say, improved telescopes, which can benefit from such quantum channels. So. And then why satellites, right? So the problem is distances. If we think of commercial systems on fiber optics, so here's a picture of the ID Quantique system, the commercial one, right? So it's very nice. Runs in fibers. This is a picture of 100-kilometer fiber optic spools in the lab. It looks like fishing line, so it's very nice. But distances are a problem, right? One can do 100 kilometers, like the commercial systems. They'll cover maybe 100 kilometers. Research demonstrations have gone further, a few hundred kilometers, and novel protocols can push that even further, like the latest developments in the so-called twin field QKD can maybe go 500, 600 kilometers. However, the distances scale exponentially. The transmission losses scale exponentially with distance, so it's really hard to go further. And of course, as everyone, as we're all aware, optical amplifiers in the sense of the amplifiers used in classical communication. They don't apply to quantum signals, right? It's essentially a cloning attack, right? If you have an amplifier, and in fact, there's nice research work from many years ago, actually now, where they showed that a standard fiber amplifier is actually an optimal cloner. So it doesn't work for quantum signals. So how do we reach longer distances, right? We want to have thousands of kilometers in the end. So the options we have are trusted repeaters, and as we know, in China, actually, they completed, they demonstrated their trusted node network from Beijing to Shanghai, around 2,000 kilometers, actually. Really impressive work. But the problem is it's trusted repeaters. So they had something like 32 nodes, I believe, 32 nodes. You know, if you go from Beijing to Shanghai, they had those stations, like 30 of those, and each of them has to be trusted, right? So it provides logistical issues. Long-lived quantum memories could be a really nice way to do this, but that's maybe also the most far-fetched one. What I mean is, what if we have memories, quantum memories, which can store entangled states for years? You have like some kind of a entanglement provider, and you have like a little credit card thing, like chip, and it's got like millions of entangled spins. You load up your entanglement, you put it in your pocket, and you walk away and just use them as needed, right? I think I actually truly believe one day in the future we will have that. However, as we all know, this is really far-fetched. So there's at the moment, no currently viable approach to have such long storage times, right? We're maybe talking hours at most. Quantum repeaters is definitely much more realistic. What that means is it has been shown that by combining several shorter entanglement distribution links and daisy chaining them in quantum repeater nodes, which include an entangling operation and quantum memories and also error correction, one can actually go to large distances in a scalable fashion. But there again, this is still quite a long way before that will actually, before a quantum repeater will actually outperform direct transmission. Is still apparently quite a long way. And the other one is satellites, where with satellites, interestingly, we can go thousands of kilometers with the quantum signals. And the reason is actually real simple. It's just that once we're outside of the atmosphere, the signals can travel without absorption. There's no more scattering. The only loss mechanism that we have in empty space is simply beam spreading due to essentially diffraction of the beams, right? And so therefore thousands of kilometers, hypothetically millions of kilometers in empty space is actually feasible. So that's the main thing, right? The losses, the transmissivity of such a channel, you go from one aperture to the other, scales as 1 over as the distance squared, and that's way more favorable than exponential. So that's pretty much the story. And now if you think about 100 kilometers or a few hundred kilometers, what does that mean? Well, here I have a picture just to also visualize the problem, right? A picture of the epicenter of Ontario, which is Waterloo here, right? And Toronto is a little further over there. Now, if we went 100 kilometers, we could maybe reach Waterloo to Toronto in a direct line, right? But actually, when talking to fiber optic providers, turns out because fiber optics is never installed in a straight line, it goes zigzag. It goes to repeater or router stations. So actually, the link from Waterloo to Toronto is closer to 300 kilometer effective fiber length, just because it's not installed in straight lines. So that clearly shows there's some issues. Okay, I do want to point out that actually what I actually think might happen in the future is that we'll have a hybrid quantum, let's say, network, quantum internet. What I mean is we'll have satellite links which provide the long haul, long distance, like entanglement distribution, and the quantum repeater nodes, where the quantum entanglement is kind of combined and extended at a large distance. And also, actually, I'd like to point out to this small study we did, in particular led by Christoph Simon at Calgary University, where we looked at the viability and even just with, for example, 8 entanglement links, at least hypothetically, with a lot of assumptions, but in principle, one could reach 20,000 kilometers. So, which means you're going across, so half across the Earth, right? Oh, sorry, not across, around the Earth, because that's 20,000 kilometers on the surface. As opposed to maybe hundreds or thousands of links needed if you went in fiber optics. And indeed, I'll mention that a little later. The Chinese satellite mission actually demonstrated entanglement distribution rate of an pair generated on the satellite and sent to 2 nodes on the ground of 1,200 kilometers. So it is kind of viable to think in this kind of on this kind of scale. But I will say this is a far future. And I like to point out there's whole other reason why to do entanglement experiments, entanglement tests in space. So which is really about the basic science and the foundational understanding of quantum states. So what I mean is, we know that there's this issue of quantum mechanics and relativity, and those 2 theories, which are the most important and powerful theories we have, right? They work really well, but both of them are actually, in some sense, they don't really go together, right? They have opposite assumptions or contradictory assumptions in some sense, right? And now there's a lot of thrust or search for, well, what is the unifying theory beyond that, right? So I'm not saying we can find a solution with that, but at least by looking at long distance quantum entanglement, we can start probing the parameter space for experiments that are well beyond what we can do on the Earth, right? If you think about it, on the Earth, the diameter of the Earth is 12,000 something kilometers. So even if we one day have a really fancy quantum internet from one side of the Earth to the other, we will only cover this kind of distance. But what if what if entanglement and relativity start, we have to go millions of kilometers or even beyond, right? So, and then the other one is velocities, right? If you stay on the ground, you only ever be able to have relative velocities that are, moderate in a way, right? But at these satellites, we're talking kilometers per second, several kilometers per second. So one can maybe start to see somewhat relativistic velocities, where relativistic effects might happen. So I think that by itself is a very interesting avenue and studying the fundamental physics, or there's gravity-induced decorrelation of entanglement. And there's another motivation to do this. Well, the validity of quantum networks, quantum computing, quantum protocols relies on the accuracy of the theory, right? If we found a deficiency in quantum mechanics, some of those protocols will have to be revisited potentially, right? Okay, so just really quick, what is the status? And I like to show this summary slide where giving an so my main point here is that quantum communication in space is real, right? By giving this kind of overview. First of all, we have to mention the Chinese satellite mission, the Meteos mission, which clearly is leading this area of research. So they demonstrated entanglement over 1,200 kilometers. They did QKD, they did teleportation, various experiments actually already. And in particular, they also recently did QKD between Beijing, so China, and a station in Austria, right? So Europe. So they covered a large distance. And they actually now even did QKD using the bell pairs. They separated over 1,200 kilometers. So they've been really pushing the boundaries there. In Japan, there's been work as well. They had an optical satellite a few years back, which was in space, and that optical satellite, communication satellite, also had a small laser QKD module, which was two lasers with different polarization states, and they were able to at least probe or test the viability of a QKD link to the ground. In Singapore, of course, I mean CQT with Alex Ling and colleagues, there's a lot of these very nice experiments on putting correlated and now also entangled photon pairs into space, into CubeSats. And so that's amazing. And we heard at the defense the other day that it actually, even entanglement in space has been demonstrated. So congratulations for that. That's very nice. There's been other proof of concept experiments from, for example, German groups around Gerd Leuchs in Erlangen, where they showed, they studied the properties of a geostationary laser communication terminal by looking at the modulation of those lasers and studying their properties on the ground. They were able to show a viable path to use that for a quantum communication. And in fact, I believe they're now working on an upgraded satellite terminal which can actually implement the QKD protocol. Another interesting direction, for example, was from Italian group around Paolo Villoresi in Padova. They looked at signals sent to satellites with corner cubes, and they actually encoded information as well. They looked at polarization and also later on time bin encoding or phase encoding, and they send still relatively bright signals to the satellite, but by the time they come back, they have emulated a single photon channel. So that's interesting. And also in Canada, we've been looking at, for our communication satellite hardware, built prototypes and so on, and actually by now it's not so recent anymore, it's more than 2 years, we demonstrated our system on an aircraft, showing the viability by sending signals from a ground station to the aircraft. So there's really a lot happening, and this is only a summary of actual hardware that was built and somehow demonstrated. And there's a lot more happening and in the works, including the mission that is also, which has a participation from here, right, with the UK Singapore quantum satellite mission that's in the works, and many others. So in Canada, we also have a quantum communication satellite mission. It was announced 2017 by the federal government. They had a line item in their federal budget, which was actually really nice. It said they want to work on quantum communication in space, quantum encryption in space, with the Institute for Quantum Computing. So that was quite impressive. So it took about 2 years to get everything lined up, but actually, indeed, in July, this July, the industry contract was put in place, and it's now been awarded to Honeywell in Canada, and they will implement the satellite. So the idea is to build a quantum receiver in space. So this is a simplistic block diagram. We have a telescope which will receive the photons sent from the ground, and they'll be analyzed in a polarization analyzer and essentially time tagged. That's pretty much the concept of the satellite. While the idea is that on the ground, we would have a more complex system. So in particular, we can switch in and out different types of quantum transmitters. We can have different types of sources, like entangled sources, weak coherent pulses, but we can also think of single photon emitters or quantum memories. And because it's on the ground, we have a lot of flexibility to use the latest and greatest. We can have different ground stations, different ground station technology as well, and thereby maximize the scientific, let's say, benefit and results of the mission. It's currently underway, and the launch is anticipated for late 2021 or early 2022. That's the current baseline. So now, right, before I go there for the actual content of what I was trying to say today, I will say this design and concept is actually actually this picture is almost 10 years old, because I first pitched it to the Space Agency when I came to Canada 10 years ago. And the basic concept is still in place, and we won't make much changes because it would throw us back to, if we add features and ideas, the concept has to be revisited. So we're going to stick with this. However, in the meanwhile, things have been progressing. So we're looking at, what are novel directions that we can explore for this quantum communication. And so in my lab, over the past few years, we've been looking at a few such directions. One was alternative encoding for the qubits, so other than polarization states. Next one was looking at novel protocols, such as reference frame independence for QKD, which will help us in aligning our telescope system. And the third one was to look at Hongo-Mandel interference for long coherent laser pulses, with the intent is to study the viability of free space MDI QKD. And I'll try to give you a bit of insight into those questions or directions. The first one is about using time bin or the time bin / phase encoding. What's the problem? So first of all, there's this kind of myth or general kind of statement, of which I was also a believer and a proponent. You can only use polarization encoding in free space quantum communications. So that's the mantra that I've been living with for many years, and it's true. It's a true statement. So it goes back to even early days of laser systems. So this is a paper from 1969 where somebody used a Heaney laser, 632 nanometers, right? So again, this is early days, and sent it over a roughly 1 kilometer horizontal link and studied the quality of polarization in a turbulent atmosphere. And indeed, the depolarization was 10 to the minus 7 to 10 to the minus 5, depending on which angle. Essentially, that was the noise floor of the instrument. So the conclusion was that, well, turbulent atmosphere simply does not impact the polarization state, right? Or at least in the optical range of the EM spectrum. And so based on that also, and it is fine, right? Even if your wavefront is all kind of distorted and messy, polarization will be good. However, when building the prototypes for our satellite project and the ground testing we did, we more and more noticed the challenges of building the optical systems, the transmitter and receiver, which preserve polarization, right? It's a real. I know it sounds like people would say, oh, it's just an engineering problem, but it's a real fundamental engineering problem. It goes back to the those nice equations, the Fresnel equations. No matter what you do, any beam that is reflected on a surface will pick up a phase that depends on the angle of incidence. So, for example, if you think of a telescope such as a Cassegrain type of telescope, very standard. However, there's a curvature here, and the rays hitting the telescope, the mirror, will pick up a different angle of incidence depending on where they hit the mirror. And as an effect, there'll be a radial birefringence that will be picked up. Now, I will say right away, it's relatively small. In particular, if the telescope is relatively long, it's not detrimental, right? The polarization error is well below, let's say, 1%. So typically, it's okay. However, if you want to build a telescope like on a satellite, you want to have a wide but short telescope. It does cause, you start running into problems. But then now this is just like a straight geometry. It gets much worse if you start having folding mirrors or even tip-tilt mirror, which is fast moving, and we require actually fast compensating systems. So we had to spend a lot of effort in our prototypes to have custom designed coatings which can actually preserve polarization even for different incidence angles, and it never works perfect. You can only find a balance. Okay, so now, right, so, but what about this time bin encoding? So in fiber optics, this is well established. People know. The one benefit is when you use it in fibers, you don't have to care about your polarization state. In free space, the issue is, well, a beam is distorted, right? It gets picks up the turbulence and gets modulated. So now why does that matter? Well, the problem is you have a Michelson interferometer, right, which is asymmetric. So for analyzing time bin states, you want to measure, you want to interfere the photon signal at an earlier time with a later time. So, and the easiest way to do that is to build an interferometer where there's a long path and a short path, and at the output one can get the interference. However, when you look at the geometry, if let's say you have an angle of incidence that is changing, you will actually pick up a different phase and also a beam walk-off that depends on this angle. So that's already indicating that there's a problem. And indeed, there is. So this is this walk-off, right? And that reduces your visibility right away. And now, this is now just like let's say ray optics, but let alone if you have a distorted beam such as this one, right? So things get quite bad if you just have a flat optics, right? So then this was out there. Now the remedies are quite straightforward actually. One is, well, you just couple your light into a single mode fiber. You're projecting into the single mode, and you're kind of throwing away all of the other modes, and you're good. Yes, that works. However, the coupling efficiency can be really low. The other one is adaptive optics. You can, at least in principle, you could have a deformable mirror, let's say somewhere here. You can correct for those wavefront distortions, but then that's a complex system which may not even work to 100%, depending on the amount of turbulence that's happening. Turns out, though, there's an interesting fix using just passive optics, which actually goes back to the 60s, which was also found when people started doing Doppler interferometry. And I will also say we discovered this earlier work only after we completed our own discovery. Actually, in the paper submission, we then got reviews back saying, "Hey, what do you want? This has been around for so long." And the reason I also say we didn't find it is because people called the name at which it's known in literature is FieldWidened Michelson interferometer. So I did not assume that or know that. But once you know the search term, you will find lots of research on this. So what's the idea? Well, it's easier to see on this example. You have a Michelson interferometer, long path, short path. The trick is relatively simple. By inserting a relay optical system, you essentially create an image of the beam front, the wave front at this point. So the beam travels this way, comes back, and you create a one-to-one image of the beam that is returned back, and exactly at this position, at this plane. So it's called AM in this picture, which means apparent mirror. So it turns out when this kind of image plane position matches exactly the same distance on the real mirror of the actual shorter arm, in the end you get a perfect overlap of your two beams, despite the one in the long arm obviously traveling the distance. So you get the best of both worlds. You get the longer time path length, plus you get the one-to-one image. And there was a patent from a person called Erskine in US, and they also, so the primary application here was doing Doppler interferometry, measuring an object in such as a star in space, and using this building this to build a white light interferometer which would be at a telescope, and using this white light interferometry to measure the presence of planets, which would cause a Doppler shift of the sunlight. And there's many variants of that geometry. And then there's another actually neater and simpler way as well. Is simply you have an interferometer, but then you have different refractive indices in the two arms. Oh, sorry, I pressed the wrong button. Different refractive indices, and however, if the refractive indices fulfill this relation here of distance over refractive index in each arm, the angular deviation cancels, at least in low order. And indeed, as a function of angle, you can get your full visibility over quite a wide range of angles. So those are the two kind of options to do this. And we then went ahead. Now this is before we knew those other works. We started this in 2013 actually. So here's the first version of such an interferometer with this interference, and we took it to the test right away. This is a Gaussian beam, and this is the angle of incidence. Without correcting optics, it just drops. So the black dots are without correcting optics. With correcting optics, it stays high visibility as we tilt the beam. We then sent the beam through multimode fiber, so it gets really ugly, 2,000 modes roughly, and also the visibility is just constantly high. While without a correction optics, even at 0 degree angle, is just a low, let's say, visibility. Now, at the first we had 93% visibility, and then later on we built a better version, close to, so 97 higher percent visibility. Now we had symmetric optics, so which helps a lot. This is actually the actual photon beam from entangled photons measured on a camera as a function of incidence angle. You can see this is one of the interferometers we used in an outdoor experiment. It's in a box, so it's isolated for stability purposes. We then put this to the test. This was done in 2018, where we built a setup where we sent our time beam signals over 1.2 kilometers outdoors at night. So the way the experiment was done is the following. We used our polarization-based QKD source and sent it through an interferometer. So this is all single mode fiber, so we can just use a standard unbalanced interferometer where here's a 785 nanometer pulsed laser, the modulators, and we convert polarization states to time bin states, because in our lab we didn't have a ready-to-go time bin source, so we just converted the polarization states to time bin, and then sent it across into a telescope. The two time bins, early, late, they were separated by on the order of 1 nanosecond or 1.5 nanoseconds, and received on the other end. And now this is where the beauty already showed up. The receiver was a simple lens with a multimode fiber at the output, and that multimode fiber was then coupled into our unbalanced interferometer with these lenses, and then the photons coupled out into the detectors. The beauty is you no longer have to worry about your beam, your focusing. You just go into a multimode fiber, and a few meters of multimode fiber will do the trick. And this is the results here. To make our point, we also sent polarization states at the same time and did a polarization tomography. The polarization is all over the place, right? While the effective Q-bar for the time bins is always relatively low and constant. It's really impressive. We converted, so this is a screenshot of our software. This is a timing histogram, and we can see the three resulting time bins in coincidence between receiver and transmitter. And the interference is the one where in the middle, right, where the superposition states can be detected. We also looked at this refraction-based analyzer with the glass, with this condition for the glass and the refractive indices. In our experiment, we happened to have a 12 centimeter cubed piece of glass and stuck it into two interferometers, and indeed it was amazing. The postdoc working on this, he couldn't believe it because he had spent 2 years or something building those relay lens systems to get them to work. And this we built in 1 day essentially, right? Just sticking in this piece of glass, and it worked right away. So he was a little, frustrated, but it was also impressive to see, right? It's just amazing. And indeed it works. Oh yeah, and this goes back to those earlier papers from, I believe this one is from 1960s or 70s, where they built a Doppler imaging interferometer using this kind of same trick, different refractive indices. And I would like to point out, this is work, very recent paper on the archive from Daniel Gauthier and Jang-Sang Kim, where they built an integrated version of such a glass interferometer in a nice integrated package. So that's the interferometers. And one day, so how could this be used, right? Even for the satellites. Well, now that there's a viable way to send, time bins over free space, we can think of doing a nice time bin interferometer with a satellite, for example, such as this so-called, they call it the pizza slice interferometer. So because the satellite, if you have a delay between your 0 and your 1, your early and your late, the satellite will move a little bit during this little, even if it's some nanoseconds, it will move. And effectively, you get a really tiny slice of area that is covered by this interferometer. And one can hope to see, effects of even the gravity under this area. So that was one. And the other interesting recent result was this reference frame alignment. Now, going back to polarization, so I was saying one issue is this compensating or fixing the polarization states, right? So it's always a big challenge in QKD if it involves fibers and other optics. You have to somehow stabilize, correct your polarization states. So this is a picture from an airborne experiment. The airplane was moving, or in the near future it will be the satellite, and the telescope here will follow the satellite. Now, our sources and systems are all in this little container, or actually it's a trailer, and there's a fiber optic, just a free-hanging cable with the fiber going to the telescope. Now, obviously, since the telescope is moving, the fiber will be bent or experience motion and change the polarization. Now, what we did here in this experiment was we built a compensator system using a tomography. We actually in real time measure a fraction of the photons and do a tomography, and then we apply a unitary operation to correct the polarization drift using 3 wave plates, and then this was installed prior to the beam is actually launched into the telescope, so free space. And it's complex and difficult to, always has to be calibrated and maintained. So what about trying to get around that? And so this goes back to some really nice ideas, which also originate from colleagues here at CQT, looking into reference frame independence, right? So what does it mean? Well, what if we can find a protocol, such as in this example, where the one basis is assumed to be fixed. In this case, they were assuming the circular polarization is fixed, no matter how you rotate the states, let's say from ground to space. Circular will always be okay, while the other 2 polarization bases will be drifting. And what they put out there is that, well, the actual quality, the quality of the channel, the purity, can be verified by looking at these correlations in these other bases, right, the X and the Y bases, because even if the states are rotating, if the purity of the state is high, then it will still show a good high quality entanglement or high quality correlation. Even if an individual correlation can be low, the other ones will go up, right? So that was the basic idea, and it was also then later verified or implemented by Jeremy O'Brien's group, for example. So the RFI QKD. So we took a fresh look at this protocol and studied the case, a variant of this, where one side only has 4 states available. Right? So that's what we call the 4-state protocol. Now, why was that relevant to us? Well, if we think of our satellite, we wanted to keep the resources low. So at the moment, we have 4 polarization states, right? The horizontal, vertical, and diagonal states. And ideally, we didn't want to add more detectors and analyzers. So we looked at a version of the protocol which has, 6 on the bottom, on the ground side, we could have a 6-state analyzer or state preparation, while the other side has only 4. And indeed, it turns out, at least conceptually, it's straightforward to see that even though I only have 2, so because I have 6 and 4 already, I only again end up with 2 correlations I can look at between the X and the Y bases. But it turns out that even then, this correlation function can be constantly high or constant 1 under this variation of this phase due to the rotation, right? So I will also say that, so essentially, by looking at this correlation of this C, that even if C, once C drops or deviates from 1, then we know there's insecurity or we have to be cautious. So, and this was done in collaboration also with Norbert's group, who put their numerical simulation for QKD and a security assessment of QKD towards this problem. So intuitively, this was like straightforward to see that we're still able to measure or extract the purity of the states, right? Even with these limited measurements, but they also ran the code which would scan the whole parameter space and verify this security. And at the same time, the assumption is that the set basis would be fixed and can be used for the key exchange. So we did an experiment in our lab. So this is not in free space yet, but we're working on that, where we used an entangled source, a Sagnac type entangled source that we had. And we built Alice in a 6-state analyzer, and Bob has a 4-state analyzer, right? So 6-state analyzer measures all 3 bases. And to mimic this kind of reference frame issue or problem, we actually sent the 2 entangled photons through PMF, polarization maintaining fiber. So what that means is standard single mode fiber is just rotation symmetric, right? And each polarization is equally, let's say, propagates equally, while polarization maintaining fiber has an asymmetry in the cladding of the fiber, which causes one axis of polarization, so 2 axes of polarizations. It breaks the symmetry, and it kind of decouples the 2 polarization modes, and they can be maintained actually in the fiber. The downside is there's a huge walk-off. So the fiber itself cannot be nicely used for entangled photons normally in the normal situation because this walk-off is way beyond the coherence length of the photons. Even a few meters, or even actually 1 meter, would just decohere the photons. So now what we did, however, was have 2 such fibers of equal length in each arm, and then turns out, due to the entanglement of the photons, the birefringence actually compensates each other, right? So that's the first kind of nice trick that we made use of. Although that's not a requirement for this protocol to work, but a nice feature we could use. So what that means is that the horizontal vertical states that were propagating were actually fixed. They didn't move. While the problem is that the diagonal or circular bases, of course, they would pick up a huge relative birefringence from this fiber and be pretty unstable and also drifting. And so now, however, the idea is, in this situation, we don't have to care about that anymore because we're implementing this reference-free protocol, right? And which can take care of the verification of the security. So in the end, what we end up, we have a birefringence in our quantum state, if we think of this entangled state, which manifests itself in this phase. And the only condition we require for this to work in the end is that this phase drift is let's say small compared to the measurement time or the photon count rate, I should say, that we're looking at, right? So what it means is, if we can assume the phase is constant over a certain time window, let's say per second basis, then we'll be able to run the protocol. So here's some of the data, and again we're looking at so we see the correlation values here. We have the set basis, which is the magenta here. It's always down here. It's always constant, and we're looking at time, right, of 2 minutes or a few minutes. While now the other bases, the XX and the YX, those graphs are, you can see those correlations are drifting around and moving. Yeah, that's a question.
Basically, polarization maintaining fiber, they wire changing the walk out. So how can you imply long distance communication?
Well, we're looking at a few meters. You're right. If you went to long distance, you mean like hundreds of kilometers, maybe? Is that what you meant? Yeah. I mean, in principle, you could have some kind of compensation. You could. So one trick is, and we also tried that you have one fiber, and then you have a second fiber, same length, and you rotate it 90 degrees. That's one way how one can compensate the large walk-off. And the other thing we were trying to do is, so the large walk-off has to be compensated somehow. We solved it by having symmetric birefringence in each arm of the entangled photons, which can also accomplish this. And the beauty is, though, we don't have to worry about the phase because the final adjustment of the phase, because we're using this reference-free protocol. You can see the bases, they still pick up this correlation and they drift around. And the red curve here actually corresponds to the phase in the entangled state that we extracted from the correlations. However, when we then go and plot the C parameter that I mentioned earlier, right? This is the blue line. Then it's always pretty high, close to 1, right? Even though this rotation happens. So that's very nice. And indeed, we were then we also looked at purity with a state reconstruction. And then we extracted, based on this data, we extracted a potential secure key rate, which was essentially, this is the key rate, essentially, some constant, over this whole drift. So that's very nice, because this would mean, by using such an approach, we no longer have to have active polarization compensation. We just connect the source to the telescope with our fibers and ready to go. That's the beauty of this protocol. So I want to point out, I don't have it up here, but there is this is also recently on the archive. I have it here. So. And then lastly, and I see that time is essentially up, so I'll have to go very quick on this one. This is something we've also been working on for quite some years now. The idea is, okay, can we do MDI QKD in free space? So MDI QKD, what that means is, here's the basic concept. So it's about improving the security of the detectors, the measurement devices. So when looking at side channels and hacking of quantum devices, QKD systems, usually the detectors are the most vulnerable point, or have been, because detectors, for example, can be blinded and hijacked and hacked. Typically the sources, the photon emitters like ALICE, they can also be hacked as a Trojan horse attack and so on, but they're less susceptible, say. Now, people came up with, in particular around Hoi-Kwong Lo, but also other colleagues, came up with a nice approach using essentially the ideas of entanglement swapping to get around this problem. And the idea is you have two transmitters for ALICE and another one for Bob, each creating, for example, polarization encoded photons, sending them to a local state called a local station Charlie in the middle, which performs this Bell state measurement, projects the two photons onto an entangled state. Of course, they're not entangled, right? So this is just an entangling operation. Looks at the kind of, think of the parity of polarization between the two states, and sends this information to Alice and Bob. Now, Alice and Bob, because they know what they sent, they can then infer the state that Bob must have sent. And that's how Alice and Bob can establish a secure key. Now, why does this help QKD? Well, if now it's now been shown or accepted, widely accepted, that even if this entangling operation is owned by Eve will not be able to mimic or send out information in any way that will compromise the information that Alice and Bob has. So of course, Eve could deny the service, right? Deny the service, but not actually gain the information. So that's why it's secure. So against this measurement device hacks. So that's very nice. And in fiber optics, there's been multiple really nice demonstrations now, and it works. Free space is not so clear. In particular, if we think of moving systems like satellites, because the channels are inherently unstable, right? Most of all, the travel time of photon pulses is not a constant. So this is a picture from one of the Italian group's experiments, sending laser pulses to a satellite, and here they plot the range. This is like 1,000 kilometer and so on, right? and over a certain time, a few minutes, and the satellite is coming closer and then going further away again, right? So we have a huge difference of travel time, and this causes a big headache for Alice and Bob. If they want to make sure that photons interfere at the entangling operation, it's actually very, very difficult. And so that's the main challenge, I think, for free space MDI, apart from other problems like mode distortion and so on. I think that the timing one is the real problem. So we looked at that by looking at, so rather than having narrow pulses and trying to overlap them, going the other way around, having long pulses and using the detection time to define the time of the coincidence. So that was the basic idea. So what we then looked at was, well, how does it look like if we look at Hongo-Mandel interference of continuous wave lasers, right? Where with, let's say, very long coherence time, and then what if we modulate those lasers, right? Let's say we apply a square wave modulation. In this case, we looked at polarization, and the main question here was, which in hindsight might be obvious, but at the beginning it was really not obvious to me. So if you think of two square waves, and we don't know when or how they overlap, right? But we let the detector time tell us, now we had photons, and then we try to infer from Alice and Bob's times, where the pulses would have been. And interestingly, and that's the main message. So we did a rigorous theory also around this. It doesn't matter how much overlap your wave packets have. You always get the perfect Hongo-Mandel visibility if your time resolution is good enough. So it's very interesting. It turns out when you look at the Hongo-Mandel, so Hongo-Mandel interference means the interference of two photons. The actual wave function, the envelope function doesn't matter anymore. Interestingly, it's almost confusing, but you can get the full visibility. So what it means is, even if the pulses only partially overlap, you can get a full visibility in that overlap area. So so for example, if a square wave modulation, you would see the full square wave visibility. However, it's modulated by some time delay and so on. And we tested this in a setup, and one result is here. As a result, we have the square waves. We change the delay, and indeed the visibility goes up and down, follows a triangle as expected, right? So the coherence time was like microseconds. The modulation of our laser was some nanoseconds, and as we scan the delay between the long arm and one and the other arm, we can see the Hongo-Mandel visibility go up and down. We also did a time-resolved Hongo-Mandel, and we're able to actually infer the overlap and the structure of the modulation out of the signal. So the scale here is a few nanoseconds. So this convinced us, just to finish this convinced us that indeed this method and trick would work. So of course this was only first proof of principle, very bad performance at the moment, but there's at least a route to use this trick in an actual MDI system. So summary, I hope I gave you a bit of insight in this quantum communication in space, and also advertise our Canadian quantum satellite mission, and gave you a few pointers in some new developments for free space quantum communication. And in particular, I want to point out that this is a joint effort of many years of working in a team of many people, and it constantly changes. This was only about 2 years ago, this picture, but already now there's like 75% turnover of the group. And over the years also, we've had multiple Sorry?
That's not a good sign.
Not a good?
Not a good sign.
Not a good sign?
Yeah.
Well, but students have to finish, right? Isn't that a... So don't your students here also finish, right? Yeah. Yeah. Okay. And also many, many collaborations from funding partners and industrial partners to make this happen. And indeed, there's positions and opportunities for postdocs and graduate students if there's interest. So thank you very much.